these are the equations to be proven, the equations of motion. So we're gonna start by saying A is equal to dt over dv, right? As we know that acceleration is equal to the rate of change in time, dv over dt, man, it's equal to the rate of change in velocity over time. How to interpret this is to do like this. This is a very tiny change in velocity over a very tiny change in time. So to continue this, we're going to say A dt is equal to dv. Then we integrate both sides. When we integrate both sides, we take A as a constant because A for a free falling object is equal to g, which is 9.81. Then this will be AT, which is equal to, then this would be this would be VF minus V initial, as this is from a initial velocity to a final velocity, and this is from 0 time to whatever time. Then VF equals to AT plus V initial. The first one is proven. Then now we're going to integrate for the second one. Okay, the first one is proven. Then now we're going to the second one. Actually, yeah, we're going to prove the second equation. So proving the second equation, we know that V velocity is d change in distance over change in time. Then we do this Vi plus AT. Then we integrate both sides. This would be ds, which is Vi plus AT dt. We integrate both sides. This will be from initial distance to final distance. Then this will also be from 0 time to final time. Then ds will be s, which is from initial distance to final distance. Then again we do for this one, which is Vi plus AT from 0 time to final time. Then we say final minus initial distance, which is equal to, when you integrate this, it will give you half Vi squared plus it's gonna give you VIT plus half of AT squared, half of AT squared. Then minus 0, because when you substitute 0 to everything that is here, it's gonna give you 0. Then this is change in distance is equal to VIT plus half of AT squared. Then the second one is proven as well. Okay, so now when you want to prove the third one, of which is this one, we're gonna start taking it here again. Taking A is equal to dV over dt. As I told you before, this means tiny change in velocity over change in time. But you can also do this dV over dt times ds over ds. You haven't changed anything from your equation because this is 1, but you can do this dV over ds times ds over dt. As you know, ds over dt is equal to v because this is velocity, distance over time. Then this will be dV over ds times v. Then this is your A. Now when you want to integrate this, you're going to say A ds equal to v dv. This is a constant, remember. Then we're going to have, when we integrate both sides, you integrate from initial distance to final distance, then from initial velocity to final velocity. Then you have AS then equal to AS from initial distance to final distance. Then you're going to have a half of V from initial velocity to final velocity. Then when you substitute here and you substitute here, you're going to have AS final minus AS initial. Then you're going to have half final velocity minus half initial velocity. Then you take A as a common factor, then SF minus S initial equal to half VF minus half V initial. Then this is A change in distance. Oh, you can multiply by 2 to get rid of this half. Then this is with 2, then this is final. I forgot the squared here, and I forgot the squared here as well, because when you integrate, you half, then you raise by 2, then by initial squared. Then we know VF squared is equal to VI squared plus 2AS change in distance. Then the third one is proven. Okay, now I'm gonna take the distance of the table. This is where the free falling object is gonna fall. So this is how I take the distance. This is 9 centimeters exactly. 9 centimeters exactly. So then I'm gonna take the object as it has zero velocity. The final velocity we don't know. We're going to calculate it there by using the equations of motion. So yeah. Okay, as we have done the practical work, where we know our distance, our delta S is equal to 9 centimeters, which is 0.09 meters. Then we want to know the final velocity of the ball and the time it takes to hit the ground. We know our initial velocity is 0. Then to know the time, we're going to have to use the second equation, which is delta S is equal to VIT plus half AT squared. This A, as I've said before, is equal to 9.81 meters per second, as it is the gravitational acceleration. Then delta S will be minus 0.09 meters. As the distance decreases, so we'll put a negative sign there. Then initial velocity is 0 times t we're looking for, plus half negative 9.81 times t squared. Then this is 0. Then 0.09 times 2 gives me minus 0.18, which is minus 9.81 t squared. Then divide by minus 9.81, divide by 9.81. Then t squared equals to 0.018345. Then we want the square root of the time. Then t is equal to 0.14 seconds. Then after we've calculated the time, now we can use the first equation to find the final velocity, which is Vf is equal to Vi plus Gt. Then our final velocity will be equal to 0, as the initial velocity was 0, minus 9.81. The time is 0.14 seconds. Then we know our final velocity now will be equal to minus 1.329 meters per second. It is negative because it's going down. Then we found our final velocity by proving.